Welcome to Design Hub, Heavy Machinery. In this fourth chapter of the Euro 7 playlist, we will discuss how exhaust after-treatment system design is impacted by the Euro 7 emission norm. In earlier chapters, we covered the scientific shift in Euro standards, the expansion of the emission control window, and the evolution of diesel combustion systems under Euro 7. If you have not seen those videos, you can find them in the Euro 7 playlist on my channel. Euro 7 introduces a major change in the philosophy of exhaust after-treatment design. Instead of focusing on emission compliance only during a limited certification test window, Euro 7 requires emissions to remain controlled across the entire operating life of the vehicle, under real-world conditions. Earlier Euro standards assumed that after-treatment systems would operate close to their original efficiency for most of their life, and degradation was treated as a secondary issue. Euro 7 removes this assumption. It explicitly requires stable emission performance across wide ambient temperature ranges, frequent stop-and-go urban driving, long idling periods, high load operation, and extended durability periods. As a result, aging behavior, catalyst deactivation, and long-term thermal and chemical stability become core design requirements, not just validation checks. Particulate filter systems are among the components most affected by Euro 7. Diesel and gasoline particulate filters must maintain very high filtration efficiency while handling both temporary soot loading and permanent ash accumulation. Soot loading affects regeneration frequency and required exhaust temperatures, while ash accumulation slowly reduces usable filter volume and increases pressure drop. Higher back pressure increases engine pumping losses, shifts turbocharger operating conditions, and can worsen fuel consumption and carbon dioxide emissions, indirectly influencing other regulated pollutants. To manage this, engineers optimize substrate parameters such as cell density, wall thickness, pore size distribution, and asymmetric porosity designs. Advanced materials, including high-grade silicon carbide and composite substrates, are increasingly used to improve thermal shock resistance and mechanical strength while maintaining acceptable exhaust flow over long mileage. Regeneration strategies for particulate filters also become more advanced under Euro 7. Passive regeneration must be maximized to reduce fuel penalties, while active regeneration events must be tightly controlled to prevent excessive thermal stress and uncontrolled oxidation of hydrocarbons and carbon monoxide. Filter coatings are designed to reduce soot ignition temperature and improve oxidation efficiency at lower exhaust temperatures. At the same time, long-term ash management becomes critical. This includes optimized engine oil formulations and ash-tolerant filter designs to ensure pressure drop remains within acceptable limits throughout the required durability period. Under Euro 7, catalytic converter design is strongly constrained by cold start and low load operation, where exhaust temperatures can remain below 200 degrees Celsius for long durations, especially in city driving and hybrid powertrains. Since a large portion of regulated emissions occurs before the catalyst reaches light-off temperature, converter performance can no longer be optimized mainly for fully warmed, steady-state conditions. Instead, the focus shifts to achieving fast activation and meaningful conversion efficiency at very low exhaust energy levels. This forces major changes in both catalyst structure and material selection. One of the most important design levers is precise control of precious metal loading and distribution within the wash coat. Instead of simply increasing total platinum group metal content, Euro 7 designs use zoned or graded wash coats. Higher precious metal concentrations are placed near the inlet to achieve faster light-off, while downstream zones are optimized for durability and high-temperature stability. Advanced coating and deposition techniques control metal dispersion at the nanoscale, ensuring a high number of active sites while limiting particle agglomeration. Catalyst supports with enhanced oxygen storage capacity, typically based on ceria-zirconia systems, are optimized to rapidly buffer oxygen during transient air-fuel ratio changes, helping maintain stable conversion efficiency. Thermal management becomes equally important. To speed up warm-up, catalytic converters are placed closer to the exhaust manifold or integrated directly into it, reducing heat loss between the engine and the catalyst. Substrates are designed with low thermal mass using thinner walls, higher cell densities, and optimized geometries that balance heat retention with exhaust back pressure. In addition, insulation strategies and double-wall housings are used to retain heat during idle and low-load operation, allowing the catalyst to stay above its minimum effective temperature for longer periods. Durability is another major challenge under Euro 7. Catalysts must retain strong low-temperature activity over long lifetimes and repeated thermal cycles. During high-load operation or particulate filter regeneration, local temperatures can exceed 800 degrees Celsius, causing sintering and loss of active surface area. To prevent this, modern wash coat formulations use thermally stable binders, DO pants, and engineered support structures that reduce crystal growth and precious metal migration. The result is a catalyst that not only activates quickly when cold but also maintains its optimized microstructure after thousands of heat cycles, ensuring long-term emission compliance. Selective catalytic reduction systems face especially demanding requirements under Euro 7, particularly for low-temperature NOx control. At low exhaust temperatures, urea decomposition and ammonia generation are less efficient, and SCR reaction rates slow down. To address this, modern systems use advanced urea injectors with precise spray patterns, controlled droplet sizes, and accurate timing relative to exhaust flow. Exhaust mixers and flow conditioning elements are carefully designed to ensure uniform ammonia distribution while minimizing pressure losses and deposit formation. Incomplete urea evaporation can lead to solid deposits such as burette and cyanuric acid, which restrict exhaust flow and degrade catalyst performance. Euro 7 systems therefore rely on advanced control strategies that limit dosing under unfavorable conditions, along with optimized injector placement and exhaust geometry to improve evaporation and mixing. Some systems also use dual dosing concepts or electrically heated components to extend effective SCR operation into lower temperature ranges. Ammonia slip control becomes a system-level priority under Euro 7, as ammonia itself is regulated and environmentally harmful. Excess ammonia indicates poor NOx control and contributes to secondary particulate formation in the atmosphere. To manage this, ammonia slip catalysts are placed downstream of the SCR catalyst to convert remaining ammonia into nitrogen and water. Closed-loop control systems use NOx sensors, ammonia sensors, and model-based estimators to track catalyst loading, aging, and temperature distribution. Urea dosing is continuously adjusted to balance NOx reduction efficiency with ammonia emissions. Overall, Euro 7 transforms exhaust after treatment from a largely passive emission control system into a highly integrated, actively managed solution. Hardware design, thermal management, sensor systems, and control software must work together to compensate for aging, contamination, and changing operating conditions over the vehicle's entire life. Aftertreatment systems are no longer optimized for best performance when new, but are engineered as durable, adaptive systems that maintain compliance under real-world conditions for hundreds of thousands of kilometers.